Yeah, the idea was that we would have a panel discussion because we have so many interesting people here, and you can ask them questions. But like to kick it off, I basically thought of this question: how do we formalize math or most of math? And then I sort of tried to substantiate it using all these other questions, like how it will happen. What do we need to do to make it happen? Like, do we need more people, more automation, AI, more Zulips, more blueprints? When will it happen? So Mike Beeson had this nice notion of QED singularity 10 years ago. So when will the QED singularity happen? What happens when it happens? So like, will the normal mathematicians somehow be influenced, or will they just not care, or what happens?
Is the QED singularity a well-defined thing, or is it like
No,
AGI?
No. Will it result in some immediate drastic changes or improvements in math or science? What happens when or if FLT is formalized? So do people upload it or not upload it? What's the place of math in the future of science? So it sort of plugs into Chris's talk, like, is math even relevant, or will AI take over everything? And then there are some more questions here. Do we really want to have to referee our own papers? Should formalization become a requirement for publication? One system to do them all? Why would we want to formalize most of math in the first place? Okay, so we have roughly two hours. So I suggest each of the panelists gets like 3 to 4 minutes initially to say whatever they want to say related to this stuff. Peter, please.
Right, hello. Yeah, I think that formal mathematics is probably in a very interesting state of development at the moment. Maybe when you see it as a curve, the curve might be quite steep momentarily. We should remember that it has been decades that all this has developed, so it's not coming out of nothing, but at the moment there are chances to really make an impact, I think. And I don't know whether I should go through these questions, but I'm pretty sure that Fermat's last theorem will be formalized and will be checked, and I don't know whether that's a singularity then, or will you make it a singularity? It depends on how this is sort of brought into the wider or into the mathematical public. I see that there are many developed systems around which could be seen as consisting of interesting parts, modules, and a question that I think comes up is how these various approaches can be linked together better than they are now. Yeah? So could we, for example, take something from Isabelle and do an Isabelle processing for some time, and then at a good point switch over to another system and let Lean do further work on it. Something like the introduction of TPTP, I think, was very important for the field, because then you had some interchange format which you could use for, well, at least for comparison or for systems to talk to each other, should we have other interfaces helping us. I don't know how I am on my 3 minutes, but something that I would like to say is that if we assume that Fermat's last theorem can be formalized, we should already start thinking about what comes after it. Does this mean that somebody who has Fermat's last theorem on their phone and can sort of scroll through it and perhaps even change this or that also, does that person have Fermat's last theorem then? Or the wider question perhaps is, what do we want with mathematics? Yeah? Do we want to sort of reach certain results which might be quite uninteresting in themselves? Or is this something educational or something having to do with, as they say in German, Bildung or so, general knowledge and culture and so on? And I think we shouldn't forget about these aspects. And perhaps if there is such a group together here, maybe one could already sit together and try to put this into a larger societal context.
Right.
Thanks.
Kevin?
I'm not going to talk for 3 minutes. But I can tell you why I want to formalise Fermat's last theorem, and it's because I'm jealous of people like, Martin Escardo is the person I normally mention, this person who told me that they do their research using AGDA because it makes their life easier. Whereas I can't even state most of the theorems which people are announcing at the London Number Theory Seminar. And in my mind, the main motivation for formalising Fermat is just because how can I possibly use these systems to do research when they don't understand the question?
Maybe you should not believe Martin Escardo.
No, you should.
Who knows?
No other comments? No big...
No, I don't have a big... I'm
Okay.
not a wise person.
Oh, all right.
I'm formalising Fermat's last theorem because I think it's fun.
Okay, Florian?
Let's see, so I think I have two opening statements. One would be, I'm afraid that the kind of tools we need to build to make formal math take off are like orthogonal to the tools we need to build like a good proof system. Like, the community is mostly composed of people who love working with logic and formal languages and tinkering with tactics, proof system design. And then to make the system used and successful, you need a totally different skill set. And the runaway success of Lean, I think, is a great example. Whether by skill or by luck, they got a lot of stuff right. And that was what got them users and momentum. And so this is unfortunate because I think even to the extent that we know what things we should build to make our systems more usable, we don't really enjoy building those systems. And
You are the wrong people.
and it's hard to get funding to build those tools. So. And the second statement, somewhat related, I noticed that the last days we saw Larry present the readable Isabel proofs, and Shankar showed beautiful PPS proofs, and Josh showed, I think, concise cock proofs was the word. And I must admit, I couldn't read any of those. And I make the same experience when I review papers. Like, often I have trouble even confirming that the theorem proved in the attached formalization is the same one as the one claimed in the paper to be formalized. So I think we need to invest a lot more into making our proofs readable to outsiders.
Could you read Blueprint?
That was actually kind of taking away my statement. Patrick made a lot of the points there.
Okay, Larry.
I begin with the very simple observation that we don't ask how can we get mathematicians to type up their manuscript using LaTeX. They do it because it's worth their while and it saves them work. And when proof assistance has reached a stage where a mathematician will sit down and say, I'm going to work this out using a tool of mine, and they'll do it not because they're trying to please somebody, but because it is the shortest way to develop what they're doing, to explore what they're doing, and to the consequences of their definition and to prove their lemmas, then they will just do it, and you won't be able to stop them from doing it. And as for what they need to do this, one talks about readability. Now, I have looked at a lot of stuff in a lot of different systems, and some of it is a lot more readable than others. But I think the users of these systems get used to that very quickly. So I think although coarse legible notations are a good thing to have, they are not the thing you really need to make this take off. And I am still convinced, as convinced as I was 40 years ago, that more and more powerful automation is the one thing. The ability to type in a thing and say, I'm not sure, does this follow now? And then wait a few minutes and say, yes, it's proved. That is a thing, especially if, like me, you're not always very sure of your own intuition. Say, yes, it's proved. This other thing isn't proved. Well, maybe it could be it's still true, but you're getting instant feedback, and I think the better that automation gets, the more users you're going to get.
Thank you. Mario?
I guess, so one thing that I wanted to mention is that this is I think Mikhail mentions that, like, well, there's so many papers coming out on archive all the time, and we're clearly losing the battle to, be able to formalize everything in archive. But I think that we don't need to actually do those papers. What we actually need to do is more the prerequisites of those papers, right? We need to do things that allow people to actually develop their own work on top. And the things that are being used to build, the average citation count of a math paper is less than 1 or something like this. The papers that are actually cited are a lot less than the papers that are the actual results of the research. And so if you're writing the next thing, what you need is to be able to provide that library so that people will have what they need. Now, as far as how do we get there, I think that we're already on our way. Like, I think that it's not as important to perfectly mimic mathematical practice as some people like to think. I think that mathematicians are adaptable to new situations. They do adapt to technology once you present it to them in the right way. And so I don't think that that's the major issue. I agree that, like, more automation is definitely going to be helpful for being able to make these tools more usable, and a community, I think, is really the most powerful thing. It's really it feeds on itself, and I think that is, to a large extent, the reason for Lean's success. It's a toss of the coin, how this sort of thing lands. It's really historical happenstance, how people enter and then other people enter because there are people there, right? So we just got to keep building the community, and we're doing that. So.
Okay, well, I did ramble on for a while this morning, I probably insist on the first point I had in my regrets, which is that the skill set that's needed to adjust the impedance between how math needs to be presented to be understandable by people, and how math needs to be presented to be understandable by a logical system is something that's still very much outside of the normal curriculum of people that go into math, and that it's probably the job of those that know how to do this to find a way of packaging, hiding away that skill, so that people that know about or are inventing a subject can can jump the gap themselves without necessarily having to hire a consultant to do that. Yeah, and we should be working on that, and we are pretty much so.
Okay.
Yeah, so a lot of good points have already been made, so I don't have to repeat them. One angle that I take on this is that I think of myself as working in a field whose name I've created. I call it abstraction engineering. And the idea is that math in some sense is the science part of abstraction because it deals with pure abstraction, and the engineering part of it is what we as computer scientists work on. And it doesn't mean that more abstraction is better. It means that you're trying to find the right abstraction, the right family of abstractions, the right way of putting together these abstractions in a way that's suitable to the problem at hand, in a way that creates technology for others to use. And a lot of it actually shows up in language. The readability of language is always going to be a challenging issue because anything that's new looks foreign until you get used to it, the way von Neumann said. The kind of other aspect of this is there's the kind of scope in terms of who uses it, and there's the scope in terms of what subjects you handle through formal mechanisms. And in many ways, kind of math and logic are the kind of degenerate cases of reasoning. So there's plenty of scope for reasoning beyond math. And of course, math is very important as the framework in which you can actually build models and solve problems. You might not know this, but Claude Shannon's PhD was actually on modeling biology using essentially what we now would consider state machine models, which means he anticipated DNA before it was discovered, which is amazing. So it's things like that, I think, that will broaden the audience for what we do. We can't just stay within the math circle. There's applied math, and there's ways models beyond. And next week I'll be giving a talk, which I haven't yet prepared, which I've titled "Living Inside a Theorem-Proving Universe." So my prediction is that perhaps 20, 30 years from now, it won't be considered too irrational for someone to actually be living inside a theorem prover.
Maybe upload it or
the same way that people, for example, live inside MATLAB or live inside Emacs.
You don't expect to become eternal by uploading yourself into a theorem proving.
That could be something that maybe we should do with George. And so this is, I like making these predictions. I think it may or may not work out, but it's fun to speculate about what it would be like. And in particular for computer science, I think it is really feasible to think in terms of everything, the hardware, the middleware, and so on, to have formal semantics that you can manipulate. And you actually get like bit precise, byte precise semantics for these things with theorem provers. The other challenge for us is brought up many times, which is bridging the informal-formal gap. This is something that is very difficult because there's such a broad audience. On the one hand, if you want to appeal to school kids with education, that's one thing. It's another thing to appeal to engineers who are using this to get something done. And some of what we need to look at are kind of multimodal ways of interpreting and presenting the formalizations. I think that's what's going to make it more appealing.
Thank you. Angeliki, are you ready to answer the main question of life, universe, and everything? How do we make most of math
So it's of course a very non-trivial question to be agree here. I think some excellent points have been made already, and we've had some very interesting discussions already the past few days. So yesterday in particular we had the working group during which we discussed also how to choose, the question of choosing which areas of mathematics to formalize and which theories to formalize, both from an individual point of view and from a community point of view. And I think one issue that we need to think about is how to coordinate among ourselves to make a good use of the human power we have. So I think we need a way to efficiently communicate what we're working on, what do we need, what prerequisites we need for the material we are trying to formalize, so as to avoid duplication of effort and coordinate in an efficient way. And I realize that maybe the Lean community is more organized with respect to that, and maybe we can learn from them when it comes to how they communicate via the chat. Yes, I think better coordination is crucial. So I do realize that mathematics develops in an organic way. We cannot force people to work on a certain thing. People decide to work on their own project, so this is inevitable, and I'm not saying it's wrong, on the contrary. But maybe we need to think a bit more on how to better coordinate ourselves and to make use of the resources we already have.
Okay, thank you. Any of you wanting to address or ask a question to any of the other people? Like I can obviously do that. So my question, for example, at least for me, like when I see this sort of new quote unquote lean people challenging the old Isabel and Cook other people. It's really like this interesting question about like the automation, and I know in my case the sort of AI, right? Like very versus like the human aspect, which really is, it looks like in the community like just a bit of this viral social aspect really has done like a quantum leap, if I use the buzzword. So like, does any of you want to comment on that a bit more? Like, I'm really interested. Like, obviously, I'm the AI guy, so I think AI will ultimately win this race, right? But like, the humans seem to be currently like it's a like very interesting to compare like Larry's talk or Peter's talk during the school, like showing that the perfectoid rings can be done using just vampire, right? Like just an automated theorem proving, versus like this amazing thing that Patrick was showing, like the number of projects, non-trivial projects on this tool that you created on the blueprint, right? Like it really seems to be like both these directions seem to be scaling up like crazy, and I'm impressed by both of them. Like, do you have any comments on that?
I have one comment. I think a big factor is the evangelism by Kevin. That really has been the, you shouldn't say quantum leap, you should say critical mass. I mean, if you have enough uranium, it explodes, and you were the uranium there.
But it's just so obviously important.
Yeah, but you really went for it. Evangelizing the turnstiles and the field medals winners around you, and that really has helped a lot, I think. And of course, Mario is like some secret weapon.
As Patrick is quick to point out, we would not be here without Mario.
Oh yes. And also, I think people overestimate how much coordination we do in Mathlib. The fact that we have one repository, it means that everything is reviewed and we make sure it all works together, but nobody is deciding in which direction Mathlib is going. Mathlib is going in the direction of contributions that come through GitHub, but there is nobody, not Kevin.
It wasn't the maintainers deciding you were doing sphere aversion. Yeah, it's just like you wanted to do sphere aversion.
It's not at all coordinated.
Yeah, but you still have one library,
Yes.
and most systems don't.
This,
They have this mess.
There's nothing stopping you making one library.
Except the owners of the system who think the mess is fine.
Aha.
These are as one. I have one more remark. The difference between, it's not the difference with Isabel, but it's certainly the difference with Spock, is that the community is thoroughly testable. They don't care for conservatism.
In
They
the
don't-
lean community.
In the lean community. They
Very
don't,
large.
They don't, and if you want to attract implementations, I think that's an important factor. I've said it.
Okay. No, somebody can contradict. Oh, okay. Well, feel free to. So I have these questions that I asked. So, for example, I would like to know what you think about this QED singularity in particular. Do you have any estimates? When will it happen? Like when will
what happen exactly?
Larry had this sort of.
What's the idea of the singularity? Is it that the machines take over mathematics, or is it that mathematicians start using proof systems to...
I think that was Michael Beeson's definition of it.
Yeah. The way I understood it was that at some point no one used LaTeX.
Yeah.
And now everyone uses LaTeX. There was really a phase transition in the 80s, 90s, I don't even know, but it was quite fast. When will this phase transition happen for formal mathematics? That's the QED.
Oh,
so when
so-
all
so- sorry.
mathematicians routinely use
Yeah,
something like this.
please shout.
Sorry.
Oh, who was first? Oh, James. Okay, James.
I'm saying the question whether mathematicians doing it is slightly ill-posed. The take-up of things is very sector-dependent. So if you look at the size of the archive sub-repositories, they're very different, even the fields are the same size and vice versa. Some mathematicians use archives, some groups of mathematicians use archives, some don't. Looking for the science, some conferences specialise in verified artifacts, some don't, and so on. I don't think we'll suddenly see all mathematicians using form. It's going to be very field-dependent, I think.
I think that, as someone else said, like, mathematicians use softwares because they help, right? They help them achieve a goal, and if it's not achieving the goal, they won't use it whether you ask them to or not. If it is achieving the goal, they will use it whether you ask them to or not.
What goal am I achieving with Fermat?
Well, I mean,
It's there, right? It's a
Fun.
challenge.
Yeah, because it's there, right? Because I know it's true.
I mean, there are people in this room who, derive enjoyment from the task of formalizing, and these are early adopters of this kind of software. But like, for people where that's not the goal, where they use it like they use LaTeX, where, most people don't write LaTeX because they enjoy it, right? There are some people who do, but they're writing the macros and whatever. But the rest of us don't, and we use it because it actually we derive other benefit from it, like being able to typeset our papers or like show things off to other people and look good for journals and all of these sorts of things. It's a tool to be used for that purpose, and so we need to get these tools to the point at which they are proof resistance and not proof hindrance, right? And it's very domain dependent, the degree to which we're there, right? Like some of this like infinity category stuff or like the AGDA stuff where you're researching type theory directly, it is actually pretty close to being the assistant because it's just too much to keep in your mind at this point. And it's helping you with the bookkeeping. Whereas if you're doing, classical mathematics analysis, there's a lot of implicit context and the computer is floundering trying to figure out what the heck is going on, and this makes things a lot harder. So, I think we're gonna keep trying to improve the situation. I think that's the best we can do. I think loading up a lot of the libraries is really the key factor in being able to make it properly usable in many areas of mathematics. So I'm hoping that when that happens, that's sort of the motivator for the phase change.
Okay. So I think we should now go to.
Yeah, thank you. I have to leave at 3:00.
Yeah.
Okay, I want to say what I have to say. Well, I think we should remember Hilbert's program. Hilbert's program did not work out, but however, the fact that it didn't work out had a century of mathematics at least as a consequence. That is, I don't think mathematics will be formalized in set theory, in category theory, in topos, in any program, in anything. Mathematics is a living thing. I work in set theory. I'm a mathematician. I'm not a formalizer. I work in foundations of mathematics. I think they are great, but they only formalize parts of things. And what to do is also formalizing parts of things. You working, mathematicians are working. I don't believe there will be a QED singularity because mathematicians are not sitting idle while you are developing matlabs. I think your work is great. I'm really happy to have been exposed to some of it with Griki and Bari, and I hope to learn more at this conference. I think mathematician will be immediately clear that there are two parts of this work. One is how to check the proofs, how to check proofs, because that's a big problem that we have in the community. The proofs are infinitely long. That's why Vojevodsky, for example, started working in this, because there were mistakes in some of his work. So this is one thing. And another one is how to find new proofs. That's what we really want. We want you guys to tell us how to find new proofs.
Yeah.
Yes, so it's great to formalize whatever. It's fantastic. It's very impressive. I don't think I will read it. I'm not going to read any formalized proof because I can hardly read the proofs which are not formalized. How many people have read the proof of the full-color theoretism proof? Very few. So it's very impressive. So I think that these aspects are sort of separate, and I'm sure that they will develop both of them. But I don't see any panic. There is no Hilbert program. There is no singularity. Nobody's dying.
Okay. The machines aren't taking over. I think. Okay. Okay.
I got a question actually about that because this story with LaTeX is often used as a comparison point, but actually I don't know how it happened. So what is clear is that the current state is mathematicians use LaTeX because they don't get a choice. I mean, when we have our students, we take PhD students and we tell them, you use LaTeX and this is how you publish. So it's not true that we use LaTeX because it's good for us. We use LaTeX because there is nothing else, right, to type mathematics.
Did you remember the?
So I want to.
There used to be a time where you had secretaries and they had IBM ball typewriters and they had to switch balls to.
That was my question. So how did it happen historically? Did they cut the funding on the secretaries and then we had to learn LaTeX, or did mathematicians learn LaTeX and secretaries became useless? Well, how did that happen?
With the typewriters, the papers looked awful. Like if you read papers from the 70s, they are horrible to read.
Yeah, but the secretaries could be using LaTeX.
Well, yes. I don't know how that happened.
You remember Ziegelman?
Yes.
Also, we designed a special LaTeX interface for the secretaries, but that's
The second one is very great.
LaTeX was too complicated for secretaries, and that's why.
Was it perhaps journals forcing people?
So we should not make proof assistants too simple to use because. Sorry, Angelique.
I'm saying maybe was it journals forcing people to submit things in LaTeX form? So in the same sense, if journal editors now say, I want your proof to be formalized before I accept it, that would be a huge community shift. The question is, do we want this, or is this going to happen, or?
Yeah.
Some of the stuff is because things became electronic and typewriters were not connected. So, producing something like PDF is a prerequisite. LaTeX produces PDF, hence.
I'm reminded of a thing that I read in one of Donald Knuth's papers on the text system when it first came out, where he claimed that because you were doing your own typesetting, you would no longer be forced to write some expression raised to the power 1/2 if you didn't want to, because apparently it was cheaper to do that than to do the square root symbol. And apparently the room applauded or something like that. Or maybe I've got it wrong and it was expression to the -1 rather than dividing by it. But you had the power suddenly to make it look like you wanted. So it was a thing people wanted. And I think we have to give people something that they want. Of course, the opposite force would be if there was a really big scandal, let's say some theorem that had been proved in which everyone believed and suddenly turned out to have a really big, unrepairable error. You could imagine some force being said, you've got to deliver formal proof of your. But they couldn't. Such a force, such a demand could not be made now. But maybe in 5 years' time, it could be made.
Peter.
Well, I remember first papers to be published. That was a very inconvenient procedure. Yeah, you would, for example, write things on an ordinary typewriter, and then you had to use colored pens to indicate whether the A should be a Greek A or a fracture A or so. And so it was really nothing connected with mathematical work. It was not natural, but it was just some kind of crutch to sort of tell the typesetters on the other side what kind of letters they should use. And then this changed to LaTeX, the possibility came up, young people adopted it, etc. Well, it changed to TeX first and then to LaTeX. I don't see a similar suffering on the mathematical side. Yeah? I think if you write your math with pen and paper, that seems natural, and you don't all the time feel, oh, I should have some kind of automatic paper which helps me with this calculation or whatever. But at least in pure mathematics, you go your way, and that seems to be the right medium. Remember that people were very keen to keep, for example, these classical blackboards here. It's not that a mathematician feels that why should I sort of go to a chalk cliff and get some piece of chalk and somehow fix particles of chalk to the wall or so. On the contrary, I think this working on a chalkboard to many people, at least older people, I think, appears quite natural because it gives you the feeling of having mathematical objects in your hand. So I think to sort of revolutionize the mathematical practice on that level would require more than the introduction of LaTeX for publication purposes.
Florian was raising his hand.
I was quickly going to summarize. So I think you can say LaTeX was successful because compared to the state of the art, it was producing better results with less work. And proof assistant, on the other hand, are producing less valuable results with more work.
So what about computer algebra systems? Have they been adopted in fields where they're relevant?
Very much so.
Yeah.
Well, then we should pursue that analogy.
Jacques was...
So I used to work at a computer algebra system company. Most people probably know. And married to somebody who's still working there.
Is it Maple or?
Yeah. They're used a lot in math departments. They're used for teaching early mathematics a lot because in calculus and linear algebra courses, a lot of computation still happens and not that much proof. It's used somewhat by physicists because they have a lot of computations and various people with differential equations and things like that in simpler areas of applied math where you can first manipulate your model before you solve it numerically. It's very useful. But the truth is, do engineers use it They should, they don't. Neither Maple nor Mathematica have made any real significant inroads in people who use an enormous amount of well-established math.
Well, we use MATLAB, right?
They use MATLAB, and don't understand that doing a change of variables to their model might make it 1,000 times easier to solve. They just write down their model and solve it like that and swear that MATLAB is slow. Yeah.
So I want to object to this line of discussion, that you need to emulate something that's already successful in order to succeed. I don't think it works that way. Stuff succeeds for no particular reason or fails for no particular reason. People use Python,
which is one of the best languages. I sincerely think.
It's one of the
JavaScript.
There's a bunch of
I would find that.
So you're not going to succeed by emulating something that's successful in another realm.
Well, I think there are good analogies between the Python community and the Lean community and why they were successful.
But Python sucks.
Yeah, but
Angeliki was raising her hand.
In the sense of providing value and being successful, I want to go back to Mirna's remark when it comes to seeing value in proof assistance in the sense of finding new proofs, what you mentioned. And of course, we all know we don't have the automation for something like that for sure. But the process of formalizing in itself, it gives us a lot of new insights about the proof. And very often, I don't have any big important example, but for similar arguments, smaller lemmas, you very often find different ways of proving things, right, while formalizing. And one could imagine that in the same sense, you could find alternative proofs. Just because you are forced to explain your work to a computer, then you're forced to think about your own work in a different way. So very often when you use different tools, right, you are forced to think outside of the box, you're forced to think in a different way. So you force yourself to think and rethink proofs and definitions. Of course, you could argue that you could force yourself to do that anyway, but having to explain your proof to a computer or someone else's proof to a computer, it really does this from a psychological perspective, if you may, that you really try to think of your proof of your or your definition or your material, the mathematical material you have in hand from a different point of view, or you may find an alternative proof of what you already have, just because you are forced to explain this to a computer, and then you have to think and rethink of your own definitions and all kinds of auxiliary lemmas you might be using. So in that sense, the process of formalizing might help you to discover a new proof in that way.
Jacques Hubert. Oh, sorry. Jacques Hubert.
Yeah, I massively agree. I'm lucky enough that the kinds of stuff that I do, not when I'm building systems, when I'm doing my other work, the systems that I'm using are ready for it. And so I gain huge amounts of insight. In fact, the thing that it's freed me to do is to make wilder and wilder conjectures. Wildly false, but I learn from using the system where I'm wrong, and I get to where I want to go faster, because I'm free to be wrong. And I have this tool that gives me insight on where that wrong is, on subtle stuff. And I've had things where I was wrong that had 200 cases, and one was false. It wasn't that wrong.
I guess the point is that today this is more like the computer science formalizations, not like if, I don't know, you want to prove some hard, serious math theorems, you will probably not get Sledgehammer to really do it automatically for you. Like Larry was showing this toolkit where you could tweak the parameters and try to prove it. And it's automated to some extent, right? But like it's not like fully automated, like I plug in this and Sledgehammer will say yes or no. Like,
Not fully automated, but you can prove a lot of things using only Sledgehammer. You just have to go through, okay, here's where we start, and then this is pretty obvious, that's pretty obvious, yeah, now and if you just keep doing that, you can quite often get to your final result with just a bit of thinking and Sledgehammer and nothing else.
Yes, but isn't the issue here is that you're not getting any insight? You're basically proving, you're checking something that you already know is true, and just saying, and so you get 0 bits of information.
You don't need any bits of information.
Well, that's like, you know, insight is and the why is something true should be much more valuable than it is.
Well, if it proved it in one step, you would certainly not get any information. But if it forced you to think through how did we get there and think, oh yeah, this is the key, this actual formula is the linchpin of the whole thing, and then you've written it out, and then you do understand it better.
Well, actually, Sledgehammer will tell you which lemma it used.
It does.
And it might think of things you wouldn't have...
Yes, it does tell you the lemmas it used, and sometimes if the proof it gave you is for some reason awful or runs too slowly, it is a big hint to how you can then prove it some other way.
What I had in mind is Sledgehammer, but something Sledgehammer on steroids. So, you know, you are in some field, you know there are 15 methods, many fields have many methods, but there are some fields which really have like 15 methods, not more. Why not start trying to prove something in these fields using things like Sledgehammer, like I try now with the game, or now I try with whatever. I think this is not so far out of reach. And I think this is why Tao is formalizing conjectures and not proofs. I think he wants to use it that way.
So, you know, there are many ways of using these things, and there's a kind of broad range of applications. But ultimately, it's not about the automation. It's about enhancing human ability, human intelligence, and you know, making this knowledge actually available to more humans. And this automation can actually build up technical debt. It builds up kind of a knowledge vacuum rather than any kind of thing where just because you can generate automatic proofs of things and so on doesn't mean you're smarter as a civilization. You know, this is just something where you're kind of taking, I mean, for example, you know, maybe machines can write plays, maybe they can write poetry, compose music or whatever. That doesn't enhance your civilization much at all.
On the other hand, we eliminated computers.
We eliminated computers, yeah, but that's
the people.
That's not, yeah, that's not the kind of thing I'm talking about. I think the elimination of computers did actually enhance civilization quite a bit.
I was thinking of a more balanced view. You know, you have some proof in mind that there is some case which is bugging you, you don't know how to do it.
That's the way you wanted to assist human abilities, exactly.
I'd like to, perhaps you should talk a bit more about the social networking aspects of this. Because you talked about the interaction with the computer forcing you to explain things, but I think in a collaborative proof setting, having to explain to the other people collaborating is even more of a motivation to clarify your thinking. This is perhaps it might be the case that that's the killer app for proof assistance. Maybe not, but the people that are trying to do this might want to chime in and to as to what they think this is leading to.
Florian?
Somewhat along similar lines, when we formalize mathematics, maybe we should distinguish between formalizing, say, definitions, theorem statements, examples, and formalizing proofs. Because the former is much easier to formalize and would probably require very different languages to do it well. And of could give a totally different set of benefits. For example, connecting to computer algebra systems, connecting to Wikipedia, helping people explain stuff.
I actually tend to disagree with that. The hard part in formalization is formalizing the statements.
Not only, but I can type in the statement of Fermat's theorem in 5 seconds.
Yeah, yes. But the hard part about formalizing the proof is describing the concepts that go into the proof, not doing the work of proving the.
You just don't know the elementary proof. That's all.
The actual, and not only can some of them be automated completely, but even those that aren't the reason we didn't rely on automation for the Auer theorem was that once you figured out how to describe the relevant pieces of group theory, you also had the proof methods that came out quite effortlessly. Even if you had 4 lines of proofs for every line of statement, these were not the place where you would spend your time.
I think the difference here is between correct definitions and useful definitions. There's a big gap between those two. And George is emphasizing useful definitions.
I think Peter was before, right? Or no order?
Yeah, perhaps going back to Angeliki, I think everybody in this room, when formalizing, has had this experience that, okay, here is something that is obvious, but how do I get it right? Maybe I should sort of set up the induction a little bit differently, and then it will go swiftly, and is perhaps more general, etc., etc. But I think there is a fundamental contradictory moment here in what we are doing, that perhaps there is a tendency that one of your tactics might just be look up in the library or so. Yeah? So that in the end, this sort of playing with mathematics, having a, I don't know, 60-minute Sudoku or so to get your small step right, this will just go out of the window because the library has it already. And on the other hand, mathematics, as it is taught, is very much of repeating and repeating and repeating old stuff that has been known for generations. And we see that as the sort of, really the task of, let's say, undergraduate studies in mathematics. Yeah? And it's not quite clear to me how to square these two things. Yeah? When sort of automation is readily available, what motivates a student to really show that if you have the Peano axioms and then you want to show that addition is unexpectedly commutative also, and it can sort of, a young student can spend a whole weekend on that and maybe not succeed, and then there is fruitful discussion with a tutor, etc. This will all go away perhaps, yeah. So what do we want out of this spectrum?
This is sort of moving it to the sort of education territory also. But I think Freek, you also wanted to
I just
react
had a question to George about difficulty being the right definitions. So does that also mean that most of the time goes there, or that it's the hard part, but then you need to spend a lot of time filling in, coloring in all the proofs?
That's definitely where all the effort goes, and then you, as was pointed out, you discover after the fact that you spent all this time trying to prove something because you had not quite the right definitions, or not the general concepts that would cover everything. Well, quite often I've refactor proofs after the fact, deciding, oh yeah, actually there's this concept or this lemma that emerges from the text of the proof. And proof assistants are actually a pretty good setting to do this. I've often find myself despairing from not having the search and indexing facilities when picking up a mathematical paper I want to work on that I have when I'm in a more formal system. Because it just makes everything so much easier to use. By the way, Patrick, you really need to put a reverse index in Blueprint. When you find a definition that's wrong, you want to be able to trace where it's used to understand how it should have been written.
In some blueprints have an index and some don't.
No, you need to be able to just click on the definition and see where the damn thing is used.
Yeah, the opposite of the uses relationship.
Ah, okay. I had something like this at some point, but
I have a follow-up question. So there's dependent types here on one hand with Coq and Lean, and there's higher logic with Isabelle and the whole systems. So in dependent type tree, the definitions are actually quite important because they determine how reduction behaves. But in the whole, that doesn't, so does that mean that in the whole logics, maybe getting the right definition is not as important?
I would say so.
You move the problem in another place. You just decide which are the right simplification rules.
No, because you can completely change how a thing is interpreted. A definition in an extensional system is not committal at all. As long as it is mathematically right, you can choose to simplify it any way you wish.
So I would disagree with that. I would say that I think in both, whether or not your definitions compute, and also sort of responding to this question about where does the proof time go, I would say that most of the time goes into abortive proof attempts for earlier versions of the definition. The proof is not at all like you write top to bottom. There's over and over and over you rewrite the proof. So like the amount of time that you spend on a given line of code is not at all represented. You could end up with, on a good day, the number of lines of proof is added is negative, right?
And much as in software development, that's the most productive parts of a development are where you make negative code additions.
Well, that is true everywhere. We want to simplify things. But I certainly don't want to worry about whether I should write 0 plus n or n plus 0.
Sure, but like the way in which you frame, like,
that's not the point.
I mean, yeah, there are much more interesting issues in how you can write a definition such that like you're like a universal property versus a structure versus different. Like they can all be sort of mathematically equivalent. Like mathematical equivalence covers a lot more than just 0 plus x versus x plus 0. And even if you can prove them equivalent, that still means that you've added a big equivalence proof at the beginning of your actual proof, right? And if you might want to think about how to phrase, like, especially if it's like a lemma definition, where you don't really care about the definition so much, but you want to make sure that it's the thing that makes this lemma talk to that lemma, and you want to, anneal it until both lemmas are looking good. This is a complicated process.
So this is sort of slightly sounding wrong to me when you compare it to the mathematicians. They do whatever they want to do. They don't do, like, I really admire like George's sort of engineering, right? Like you impose a style and then you teach his whole team how to follow the style, and it works, right? Like you can formalize two books of group theory. But it seems to me that it's not what you will teach mathematicians. Like they flexibly change between different equivalent definitions of a concept.
I think that mathematicians do this too. I think they do it at a slightly different scale, but like they also, you know, when you're trying to find your way through a proof, you have to like keep trying different variations on the statements of your lemmas, trying to get things to fit together. Maybe you don't need, you know,
Well,
to be
all of
as
them are
detailed
available
about.
for this constraint solving game. Like you are choosing, like maybe it's some sort of a pre-formalization phase for you, but like the mathematician knows all these 10 different formulations, and the fact that for you just one of the paths through this sort of constraint solving space and ends up in the formal proof doesn't mean that the sort of space isn't reflected somewhere in the pre-formalization.
I think I need to talk about the definition of an epsilon regular partition of a graph. So we looked at this thing, and it had the strict subset relation and the non-strict subset relation in the same definition. So naturally, we assumed that the strict subsets were meant to be strict, and the non-strict ones were meant to be non-strict. And we got through this proof of Shumareddy's regularity lemma, and that was fine. And then we got on to its application to Roth's theorem, where it seemed very clear that the strict subset relation was being replaced by equality, and that clearly didn't make any sense. And after an enormous amount of fuss to say, well, it actually doesn't make any difference whether it's strict or non-strict, except in one degenerate case, which surely can't matter, except that it turned out we couldn't see how to prove the degenerate case. And then when it came back and they said, oh, well, yeah, this is combinatoric, so basically the two relations are the same. But if you allow the non-strict subset definition, then all the other proofs have to be modified to handle a certain other degenerate case, which fortunately was quite easy to deal with. But all of that was because we didn't know what the fucking definition was in the first place. And I could have probably just asked Tim Goward or something, but I didn't want to bother him. You know how it is, you just go and keep banging your head against the wall. So in that sense, it's nice to know what the thing actually is.
So you agree that getting your definitions right is right?
Of course it's important, but we don't have to worry about...
You should not be too strict about what it means to be a definition. Sometimes you give one point of view and you give a certain number of points of view on how to work with a certain concept, and this is what is used as a definition.
Oh, we certainly distinguish a thing which is the definition, you know, to be conservative. So we say we define it like this, and yeah, we can then formalize different views of it, and of course, normally we're not expecting anything to be computable.
Perhaps concerning definitions or also formulating certain statements, I suspect that with many of the things that we are doing here, we are practitioners or are knowledgeable about a certain system, and we have the workings of the systems a bit in our head, and do certain statements because we know, oh, it will have difficulties doing it this way, so we do it the other way around. Yeah, so I don't know, quantification with 3 variables is perhaps quite hopeless, so maybe I split it and have a subdefinition or so. So it may be that in our practice, this sort of knowing how it will be sort of processed within the system is sort of important. And if we want to sort of give such a system to mathematicians, they will automatically sort of run into problems because they don't know about these internals. Yeah? So is that something that you
I think it's not as system dependent as you think. The main difficulty is that if you are going to do a formalized proof, you have ultimately to take care of all the details.
Mm-hmm. But how?
Well, you have to organize them. And that's the part that is the part that's harder when you go from completely informal to more formal, is that you're forced to organize the details in order for them to remain manageable. And that tends to be true regardless of the system you have. Perhaps if ultimately you have a super powerful automation and somehow all of the details can be handled automatically with no loss of performance, this might not be an issue, but otherwise that's the issue. And ultimately that's also where the value comes from. That because you have had to look into the details, you're forced to discover structure which you would have overlooked, saying, "Oh well, yeah, this is just something I'm not interested in. There's nothing to see there." And lo and behold, when you're forced by the system by the fact that you ultimately want to prove everything, you're forced to look. You discover, oh yeah, actually there was a right way and a wrong way of doing this. Which you offer to discover in a very painful manner.
So I want to react to what Peter just said, which, so for 2,000 years we've had the declarative reading of mathematics up front, and the procedural reading has been kind of in the background, implicit. Here, even in informal mathematics, the procedural reading actually is important. When you prove a lemma, you're often creating a device for constructing certain kinds of objects, for mapping from one problem space to another problem space, and your each little thing that you have out there is a way of constructing other further objects or further procedures. And this isn't something that's peculiar to formal mathematics or to a specific system of formal mathematics. It arises even otherwise, although it's kind of more emphasized more when you have the peculiarities of a particular formal system. And this, I want to, in this context, emphasize a point that George made, is that the value here with mechanization is that you can maintain a body of knowledge. You can maintain the consistency of the body of knowledge with respect to change. You can maintain the growth of the body of knowledge. You can say that, okay, if some kind of growth forces you to revise something, that you can propagate the changes consistently. So it's this kind of, I distinguish between the intrinsic and the extrinsic value of automation. I mean, some of this is the intrinsic value. So when you have all this, it's useful to you in maintaining the consistency of your own body of mathematical knowledge. The extrinsic value of this is that some of these devices now can be made available in a form that others perhaps who might not be interested in how the sausage is made, they can make use of it in interesting ways as well.
I had a quick comment on what Josef. Like, I totally agree that when you dig deep and when you optimize things, you have shown it, I don't know, with the hypermaps or whatever, you find interesting structures. But then, I don't know, Chris was showing this Boulogne example, and like, it works like this. Voila, like, Vampire could prove this. I'm really surprised. And then we even found out that Mattis can prove this, which was like a surprise both for me and for Larry, maybe also for Chris. And the point is that we all know that this is true, and you may or may not be particularly interested in how Vampire or Mattis proved it if you work on the sort of higher level. Like, people who write automated theorem triggers, they are interested in how to do these tricks, to do that thing in the same way as you are interested to discover hypermaps, to simplify your formalization. But like, if you are, I don't know, Peter Kepke, and you want to quickly show to the lean people that you can do vector spaces or rings just with Vampire, you just go through it and you don't look at the Vampire proofs, right? So there are like different tasks or goals when people are doing this sort of stuff. And I don't know, like, what you think about these different people than you. Like, I guess your argument is that you need to engineer it, right? Like that if you don't, then it will bite you eventually, right? Like that seems to be sort of your argument for really engineering, like these.
Yeah, you really need to do. I mean, there's no absolute limit as to if you're into this and you're a perfectionist, you might want to dig as deep as possible and understand the best way of aligning the bits in every bit and every place of your structures. You may decide that yeah, there's probably some way of organizing this so that it works, and I can basically anneal the development until it works, which is might work, but might be a problem for future versions.
This is why it's abstraction engineering.
Yes. I had like one, like I think George proposed this sort of way forward, which sounded like formalization could be pushed for these big projects where people are like need to understand one another, right? Like, do you think that this is like somebody said that Terence only formalizes conjectures? I don't know. Like, but do you think this could be something like some sort of formal polymath project or some sort of let's formalize a crazy new kind of heterogeneous mathematics collaboratively? Is that like one of the big future applications of formal math?
Maybe one of the drawbacks of mathematics is that it tends to be a bit too solitary an activity. So there might be a market for making it more social. Who knows?
I'd like to mention a thing, analogy with chess. So there are massive chess databases in which is stored every master game ever recorded, which means if you are looking at a chess position and you could look it up in a database and maybe find 1,000 games in which the position had occurred, who won or lost from that position, what the next move was, and so on. Now one could imagine, of course, mathematics is not an 8x8 board, but nevertheless, many, many times people are doing a thing that has been done before, or that is very similar to a thing that has been done before. So one could imagine if a really vast amount of maybe quite routine work of previous papers had somehow or other been codified in some searchable system, not necessarily specifically in Linear Isabelle or whatever, but in some possibly somewhat less logical way. I know there's whole conferences devoted to mathematical knowledge management. And you had this tons of stuff there, and then the person who was in their own proof could say, hey, you know, that's so-and-so, 1937, you know, and you'd say, oh, right, this paper I should look at, and my proof is there, you know, that would be a useful tool.
Yeah, search engines. Like these days people will say large language models are search engines. Oh, Mario.
Yeah, maybe, yeah, if they can do that, but I don't know if they don't understand anything.
Yeah, I
the substitution of an X for a Y might throw them off already.
Yeah. Yeah.
Yeah, so I mean, I wanted to mention regarding like the new polymath. I think that formalization is actually well positioned. Well, at least, you know, there's some evidence that in Lean that, you know, we're starting to get these sort of really big collaborations, and this is really cool. I mean, I don't know how many other, like, we're really, you know, pushing the boundaries of how large and how many people can get involved in these projects at once and still sort of work together on a thing and prove a theorem together. I mean, like, polymath is a great great example of doing sort of collaborative over the internet, sort of like trying to discover new theorems and doing experimentation and all of those sorts of things. And, you know, it's exciting and it gets people involved and that sort of thing. And I think that really we can do something similar with the, like, you know, like these blueprint projects and being able to just set things up so that you can just unleash armies of people at a task and then end up with, like, you know, papers that have, you know, 100 names on the thing. That's just unheard of in mathematics.
We can be physicists.
Oh yeah. So this actually plugs to one of these questions, right? Like, what happens to the quote-unquote normal mathematicians if this sort of takes off, right? Like, how will the two cultures interact in, I don't know, track? Yeah.
Patrick,
So just a comment on what Mario was saying about polymath. So I think it's not at all a coincidence that Tim Govers and Terry Tao were just early polymath enthusiasts, are now formalization enthusiasts. So in their different ways, they are not the same person. But Tao in particular emphasized a lot this collaborative aspect, and when he gives talks about what he does with computers, he really emphasizes this, and indeed there are already projects. So the liquid tensor experiment, I think, got contribution from maybe 15 people, and polynomial Freiman-Russa was also. So the current order of magnitude is more like 10 to 20 than hundreds, but it may become hundreds. If we now look at the Carlson's project of Floris, the blueprint is 150 pages long. I think there is room for 100 people contributing. I don't know if those people exist, but there is room for them.
So do you have any idea, like you are a mathematician, somebody comes to your department and he's a co-author of 3 blueprint finished papers like this with 100 co-authors. Will you, how will you evaluate him compared to some, I don't know, Peter Kapke or Kevin Buzzard, who have proved a particular theorem and got tenure because of that? Like, what's the new kind of mathematical?
That's a very tricky question, and I think we could have a whole panel discussion about this topic. I mean, clearly the current situation, and my math department is, I think, a very conservative one, because it's an old place in an old country.
An old continent, yes.
For instance, I'm very impressed by what Bonn did when they hired Floris van Doorn, and I will have a very hard time getting my math department in Orsay doing that. I don't know how it happened here, because Bonn is the kind of the German version of Orsay or Paris with respect to mathematics, and I don't know how this miracle was.
Maybe Peter knows.
Maybe he can tell us.
I think what I wanted to say also has something to do with your question. These questions here up there talk about formal or formalized mathematics, and we at the moment pretend that this is just one uniform field, and there is basically, it's like LaTeX, right? It's sort of, and the comparison isn't quite true, because there seem to be many LaTeX here on the panel or in the room, which perhaps complicates the situation in terms of such a takeover of a system. Now, so let me tell a little bit about that. When I had to explain to my colleagues here what formal mathematics is, this question also came up. Yeah? I say, okay, formal mathematics, eventually it will take over, etc., etc.
Matter-of-factly mentioned it.
Yeah.
It's a very believable statement. It's always worth saying.
But then they would ask questions, yeah, and I said, oh, this has been formalized in that system, and there's another system, and this system is based on this, and that uses the other logic, and so on. So I think there is a big difficulty when we think of outside representation. How do we want to present ourselves? Yeah? Would we at the moment say, well, Lean is winning anyway, so shall we identify formal mathematics and Lean momentarily, or for talking to mathematicians, should we say, well, if you want to learn formal mathematics, you have to go to a Lean school or so? I mean, apart from the big systems, there are smaller systems, there's this small approach, but then there are PhD students who write their own system, and once they have got their PhD, maybe they leave academia or do something completely different. So, I mean, what is formal mathematics? How do we present ourselves?
I think most math... Oh, sorry, Christine.
No, let's continue.
I think most math departments are very far away from this problem. I mean, if I say I want to hire as a professor in Orsay, and that person who did great formalized mathematics, my colleagues will not ask, is it Lean or Isabel, or they will ask, what is the new theorem? And then if I say there is no new theorem, they like, if I say, let's say I want to hire Kevin because he formalized Fermat's last theorem, but forget about the then they would say, what is new? I mean, Fermat's last theorem has been proven by Wise. And so, what are you talking about? Stop wasting our time. So,
but if
the current status in math departments.
Yes and no, but I mean, if you then talk about more concrete aspects of that, like has happened here, then you would say, well, what would this person be doing? Would he sort of go and formalize one theorem after the other? And so there's an endless stream of certified mathematics, already existing theorems coming out of that. Okay, maybe it's a good idea to go near to research mathematics, but I think eventually you will have to be honest and talk about methods, yeah? That people in formal mathematics are developing methods that others can use, and then they are doing these methods on certain logical bases and so on. So I don't think we can sort of ignore these, that there are differences, higher order, first order, whatever.
So we took the example of LaTeX, but there is another example which is between algorithms and programming. And we know that in that world there will not be only one programming language.
Oh yes, good.
And it will be, okay, and we do not want only one programming language. And I think the analogy is also, it's not because you have plenty of algorithms which are implemented, but there still is room for people to invent new algorithms and new things. And you cannot imagine, so this is two very related activities, designing the algorithm the mathematician is doing, to be able to do an implementation of the algorithm, because otherwise it would be useless, and formal mathematics, and to build good tools for being able to program these complex algorithms. So I think we should sometimes think of this formalization of mathematics process a little bit more like this process in the computer science world.
But isn't it that, let's say, in applied computer science, you would have that, okay, I use that programming language, I don't know, to parse an input, and then I go to another programming language because that is better for handling the large amount of data which comes up, and then etc. So
That's exactly what you do.
Sorry?
That's exactly what you do.
If you're implementing an algorithm, you're going to code it in one language. Now, you might have a system combining things in different languages. But certainly my conception of an algorithm, you then code it, you write the program in one language, and you'd have to put up with any trade-offs of that language as opposed to other languages.
So, this discussion about different systems and all that looks strange to people from outside the community. Inside the community, we are exploring different parts of the design space. There isn't any perfect portion of the design space. There are always trade-offs. You do one thing at the expense of the other. And in terms of formalizing mathematics, I mentioned this Dana Scott quote that it's an experimental science. I mean, there's a lot of room for a lot of experimentation in this. How many of you know what SMT solving is? More than I expected. Mathematicians could have discovered this at any point in the last hundreds of years. They didn't.
They didn't have computers.
No, it's not a question of computer. They decided this did come up with other similar procedures, but Nelson-Oppen and Shostak did not get discovered by mathematicians for hundreds of years. Okay. So it's things like that you'll see many, many more inventions of this kind once you take the formal perspective. And that's the difference it'll make. It won't be about using this or that proof checker. It's this completely different viewpoint.
Well, it's an interesting fact that many of these tools were discovered by philosophers. So like Hao Wang with his first theorem prover, and then you had Davis, certainly Hilary Putnam was a philosopher who wrote essays. I think Martin Davis was more of a mathematician who then gave us the original SAT solver and then the refined one, and of course Alan Robinson, who gave us resolution, was also a philosopher. Though he didn't give us any executable code, but yeah.
Like you
an executable logic.
You could call them logicians. There's this
Jeremy
in logicomics where Russell discovered that he's neither a philosopher nor a mathematician.
He's a philosopher.
Hiding, right?
I had an amazing conversation with Willard Van Orman Quine.
Oh, wow.
And just about everything I mentioned, he was saying, yeah, he studied here. So when I explained resolution to him, he said, yeah, that's in my methods of logic. Indeed it is. Okay.
So sorry.
So you asked about the future polymath style community project. I think formal abstracts is still the right idea. Unfortunately, the project failed completely.
Well, failed is a strong word. It wasn't implemented, right? Like Tom sort of stopped working.
Well, it got Kevin on to lean.
Yeah, but in some sense, you could argue that I'm motivated by that. So formal abstracts was Tom Hale's saying, we just need to get the systems to the point where we can state what mathematicians are doing. And I've already said that one of my motivations for that last theorem is that we're still absolutely nowhere near. I go to the number theory seminar every week, and the question I always ask is, can we state this theorem? It's almost always not going to be
failed, but it stalled. Then I think it's still the right project.
And I'm trying to do it for number theory, for algebraic number theory. But I don't think I can do it for everything. And so we need other.
What percentage of definitions do you think will turn out to be the right ones, right? As many others have said, all the difficulty is getting the future-proof useful definitions.
The problem is that a lot of these definitions are gigantic. I don't know. They're a long way from being. I'm so far from being able to understand that question properly that I can't really say anything coherently.
For me, it's like the definition of a canonical map. Right? How do you get this right?
The definition of the crystalline Gabor representation is a well-defined thing. It's just that one thing that we didn't realise was that you have to plough through a gigantic 50-page paper containing some very delicate induction argument before you can say, well, obviously, just this, obviously something exists which satisfies this universal property. These definitions are just really big in my field.
And they rely on a lot of proofs.
And they rely on proofs.
Right. So, if you don't have the proofs, you get stuck.
No, I think Florian's argument is that you should still do it.
Yeah, write the proofs informally.
So sorry the proofs.
I think at that level of complexity, if you do that, you have a kind of 100% guarantee that you will get it wrong.
But that's not necessarily you can still be useful. Like in particular, it unblocks later definitions. This is something that I've been telling you about. Like, FLT is going to involve a ton of definitions, and I think that one of the most important things to do first is basically to write down first drafts of every definition, and they're all going to be wrong, but it's okay because we'll revise them 5 times anyway. And at least
but that's the important part of the attitude.
Right.
If you assume that you're going to get them all wrong, then you're going great.
Yeah. What it unblocks is the ability to state those theorems that are going to come later, and then there's going to be some the annealing process starts. People can start working on the theorems, finding out how things fit together, and then making modifications to the statements because of that. But I think in a lot of areas, if you just don't have any definition, you're just miles away and you're just thinking oh, it would be nice if we had this stack of definitions, and no work is getting done up there, right? But if you had some first draft definitions, then you could just be working all over.
And apply the Tarski and stuff there.
Well, maybe.
So fine. So imagine we will define this annealing process somehow chaotically or less chaotically, and I don't know, most of mathematics is formalized, and this annealing process somehow involves, I don't know, 20% of mathematicians or whatever. But there is still the crisis question, right? Why are we doing this? Shouldn't we be doing something else? Or fine, we have succeeded. How is this useful? Is it the training of the AI systems to do superhuman math, or is it ubiquitous verification? What are the selling points for it? Yeah.
Why is pure mathematics useful? That's not useful. It's nice. I mean, people enjoy it. It has some trickle down thing into practical things. But if you read Hardy's mathematician apology is very clear. You have useful mathematics and you have pure mathematics, and there are these two principles. So your question.
He has a lot to apologize for.
Come on, who knew number theory could be so useful? All the crypto people love it, and it gets crazier and crazier. Nobody could have known. That's what pure mathematics is about. You don't know, but you do it anyways.
I don't buy this argument. Speaking as a number theorist who starts every grant proposal with the statement that number theory is manifestly the most important branch of mathematics, because look at all the applications to cryptography. It's all stuff that was done in the 50s. It's nothing to do. The Langlands philosophy links elliptic curves and modular forms, and elliptic curves are used in crypto, so this is great. even though the Langlands philosophy elliptic curves are over Q, and the crypto ones are over finite fields, and they're barely anything to do with each other. But
from the point of view, of course, it's BS. But the whole point is that when people were doing it in the 50s, they had no clue whatsoever.
Right, but I don't want to deduce from that the stuff I did for 25, the p-adic Langlands program, which I did for 25 years, I find it really hard to believe because the p-adic numbers are just not a very good model of what's going on in anything, right? Kind of anyway.
As
you
for
can
why,
use them to describe the computer circuits, you know.
Okay.
as for why you,
p-adic Langland's program is that?
as for why we want to formalize mathematics, I think I'm quite close to somebody who once said that mathematics was a house of cards. Didn't you say that?
Yeah.
Yeah, and one of my postdocs, he wrote an essay called, what was it? Replication Crisis in Mathematics. So that was Anthony.
I am concerned. One of the reasons I kind of left the area was because I got concerned that maybe not that things were wrong, but that people were building on things that hadn't been published. They were building on promises.
Yeah.
And if you know, and if it's not completely proved and it's not of any use, then what is the point of it at all?
Well, I kind of think, let's say this Gödel second incompleteness theorem, which I formalized, and which is one of the more obscure proofs out there, that, and you don't have to read it because you can actually run it and you can step through it. You can step and see what concepts are being used, what the theorem, how the theorem is stated, and then if you want to look at some particular point and say, how does this case handled? You can go through and say, yeah, this
sledgehammer.
No, you can look. It's already there, and you can look through it and say, oh yes, so he's doing this. There's some very clever variable renaming going on here, and blah blah blah. And so that is, which is the trickiest case follow. Those cases are kind of trivial anyway. And one can do this for more and more things, and then when there's any really tricky proof anywhere that has been formalized, first of all, it has been checked by this utterly obdurate machine, so that's number one. And I do have faith in these programs precisely because they make it so hard to prove anything. and then you do have this thing which you can either look at, and if that's not good enough for you, you can run it, and you can actually inspect it at any point and see what exactly is happening in this place until you convince yourself that yes, this is really what's happening. And I think this gives you access to knowledge that is just not available in any textbook.
Is it interesting knowledge?
If you're worried about whether it's correct or not.
I'm not remotely worried about whether that's our story.
No, but there are some you were worried about. I think you were talking about...
I'm totally, but these are incomprehensible.
Classification of finite simplicity.
I'm worried about things in number theory that people have said they could do 5 years ago.
I'm sure you said that it was proved by 3 people and 2 of them are dead.
Oh, classification, I mean, but that's not my area.
Okay.
It's not my problem.
Someone else might worry about it.
Yeah, that's not my problem.
I mean, it would make a great project to get grad students interested in algebra, right?
You're not going to sell
a bit too hard for this.
You're not going to sell finite groups to graduate students because the area is not fashionable anymore. I think the only way we can formalize the proof is by AI and we get Isabel to read the book. I think absolutely it's probably the best system to do it.
Maybe I was rushing at the end of my talk this morning, but my answer to why are we formalizing mathematics, my main answer, I think there are several reasons, but my main answer is what I showed at the very end of my talk. Producing documents where readers can choose the level of details by just clicking on buttons to see more details where they want to see more details and not click when they don't want to see more details.
Maybe Patrick is not finished.
No, I'm finished.
Okay.
No, for me, it's more like in the age of the internet and the spread of news that are not confirmed. Mathematics is also suffering of that. A lot of people are publishing papers that people don't have time to review, and we are bringing a small stone to that edifice by saying, oh, there are places where we can add some reviews that people will trust a little more.
People are publishing unreviewable papers as well.
But sorry, because now you can just pay and then you can avoid the review process.
I think we see it in politics, but it's true everywhere where somebody has a financial advantage. If you're going to get a position because you are able to publish some bullshit, then you're going to do it. Well, maybe not you, but some people in your entourage may be doing it. We've seen it in biology, we've seen it in
AI. This
there's
is
no reason it could not happen in math.
Well, Archive has several proofs of the Riemann hypothesis.
Yes, not to mention the four-color theorem.
Or
the ABC conjecture, for that matter.
There are known examples of sort of citation cartels, where people publish a paper and cite 24 other people, and they're all citing each other, and they artificially bump up, and then algorithms compose rankings of universities that see these big citations, and they push in. This is absolutely happening
We're
already.
also serving a little in this respect.
This is already happening, yeah.
Steve.
I'm talking about mathematics.
Mathematics was taken out of some rankings because
Yeah.
a big cartel in mathematics. That they're not
Wasn't it only relatively big compared to the number of citations in the field?
Right.
So yeah, you need small citations, a small cartel.
Steve, they had yeah.
There are lots of examples of higher algebra and higher category theory where we just don't know if proofs are correct. It's complicated to check. Vladimir used to give this example of a Petrov and Blavatsky paper, published paper, right, with a coherence theorem for tricategories, which turned out, which he believed was correct for 10 years, and it turned out to have a mistake. And that has not been formalized. I mean, I think we're pretty sure what the theorem is now, but we're still nowhere near formalizing it. He had another example from his field study work on motivic homology and motivic homotopy theory, where there was also found a mistake more after that, and that has also not been formalized. I think that was when he died, that was the last thing he was working on, was trying to get up to the point where he could formalize those results and make sure there weren't any more mistakes in it. So I think there's real practical advantage to formalize, but we have to get to the point where we can do this kind of higher stuff, and it's not necessary, so I'll just say one more thing, but it's not necessarily going to happen by building up a mountain of definitions from the basic elements of mathematics. Vladimir's program had this kind of synthetic or univalent approach, which is a kind of axiomatic approach, which starts at a very high level and formalizes based on universal properties. And you don't have to build everything up and prove that it has the universal property. You start with the universal properties as definitions and state or inductive constructions or whatever, descriptions of the structures you're working with. You go on from there, and that allows you to do higher dimensional stuff without having to go through all the tedious mountain of definitions. So program there, which is still going, there's not very many. It doesn't have a strong connection to lean and other things that are happening right now because we've got our own tools that are not interacting well with the things that are being developed.
Mario is helping.
We're working on it.
I had probably one last thing to go through the panel, which may sort of summarize all these questions. And that's like, where do you think this field and math will be in, I don't know, 20, 30 years? And you each have about 2 minutes, Angeliki.
In 20, 30 years?
Yeah.
Well, I think it will depend a lot on factors that we cannot really estimate at the moment. So it depends a lot on how much people will get involved. I do think the field will continue to attract more students, more mathematicians for sure. To what extent we will have a system where we will be expected to submit our proofs formalized to journals, that I cannot say for sure. But I do believe that the field will continue to grow, and there will be more people involved and more people from mathematics, for sure, in a few years to come. Well, another question is what the effect of AI and large language models would be in the area. That again is hard to tell. So there is some work on auto-formalization at the moment. So one question is to what extent we can use such tools to speed up the normalization process, or do we want to use such tools to do we want to introduce such tools in our work or not? It's hard to tell. So,
Okay.
but I do think the field will continue to grow for sure.
No bold predictions. No concrete crazy predictions. Like 50% of math will be done formally or something like that.
Yeah, I wouldn't like to say 50% of math, but I do think the libraries will continue to grow for sure, and there will be more, because we see all these wonderful new tools that are being built, like the Blueprint tool that encourages people to collaborate more and facilitates bookkeeping for groups as well. So if you have a very big, complicated group, then it's easier to break it up in smaller pieces and maybe check them locally, or to see how different components of a group
okay.
You know, so yeah, all these tools will encourage people to work more in this area, and they will bring more users for sure. That I'm sure.
Okay, that's fine. Shankar, we will live in theorem provers.
So more of us will be spending more and more of our time inside theorem provers. Initially it'll be mostly computer science oriented folks, but it'll expand to other engineering disciplines and maybe even computational biology and so on. The formalization of math will then take place opportunistically. The bottom-up formalization is minor. I think the opportunistic one is one that will dominate.
Okay. Gosh.
I'm not sure I can state it better than that. If we make it work, people will use it, I think. Yeah. Probably the where I can state it.
Oh, okay. I expected some concrete betting numbers. You know, like 10 years ago, I forwarded like these predictions, these bets at my talk at the Poincaré Institutes. So I expect people to be provocative, right? Mario, please.
AI, you throw in AI,
Yeah.
Actually obligated to say that in 10 years human being will be replaced.
Yeah. The AI people are doing this, predicting stuff all the time, like people are bored.
The people who were using computer fluid dynamics said, oh, in 10 years from now, we are going to use all these souffleries, I don't know how all these wind tunnels to store the computational fluid dynamics papers. You know, they're saying computational fluid dynamics is just extinguishing the field. But they discovered later that they had to check their models against some truth. The ground has to come from experimental work, so you still need the wind tunnels. We're only modeling mathematics with these tools, and the mathematics that we are modeling is different from the model. So the mathematics will survive all this modeling, probably.
Okay. Mario.
Yeah, so 20 years is a long time. I think a lot of things will change, but it's extremely difficult to predict what those are. I wouldn't be that surprised if like formalization of mathematics wasn't that different in 20, 30 years. I think that it'll, like, people will keep doing big projects, and I expect that Formalization theorem will be done. But,
10 years?
How many years?
20 to 30.
You're right. One area which I'm hoping to see a lot more growth in is the development of sort of programming languages with stronger support for built-in proofs and just being able to write in a sort of formally checked kind of programming language. Right now, there's not that many offerings in that area, but I think that there's a lot of sort of market pressure towards getting better tools in that area. So, again, it's really difficult to predict what would happen in 20 years, but I'm hoping that I'll be writing in one of those languages in the future.
It's a bit like what Shankar was doing, but a lot of stuff will be done inside a theorem prover rather than in some unverified programming language, right?
Yeah.
But yeah, life is much nicer inside it.
20 years is a very long time. So when did you finish the four-color theorem?
20 years ago.
20 years ago.
Okay, so at best, if you were to look at a big example of formalization 20 years ago, it would be the four-color theorem and maybe like incompleteness theorem.
Five-number theorem?
Yeah, maybe that was done, yeah. Okay,
that's about
so
20
there's
years ago.
a few things. Whereas now, if you tried to make a list, it's already immense. I'm pretty sure we're going to see this stuff becoming ubiquitous, and I don't think it will even take that long. I don't know that the Fermat's last theorem might be done in 5 or 10 years. I know it is huge, but there are a lot of people. If you can get them excited and doing things, if you have 200 people working on bits of it, wouldn't surprise me. And if that is done, there will be a huge amount of substrate. I assume that these results could be used for lots of other things. So I do think it is unstoppable.
Try something provocative. So I'm going to say mathematicians will not understand that they have to embrace the system design and build the tools that they need. They will wait for computer scientists to build the tools for them. But computer science system design will be dominated by industrial applications. Systems are already strongly optimized for software verification. They will continue to drift in that direction. Leo is at Amazon now. The culture there will also make lean shift towards industrial applications.
Verification of AI will take over.
And fail. So formal math will be an afterthought of proof assistance. The community will be stable, it will grow, somewhat exponentially maybe, but it won't have a tremendous impact.
It will not.
Yeah.
Oh, okay. Thanks for being provocative. Shall we go in?
Yeah, so I have no idea what's going to happen. I'm confident that in 5 years' time I'll have proved a bunch of theorems from the 1980s. But whether the whole thing will scale and whether it will just be impossible to keep everything up to date, and whether we'll actually prove that all of those theorems, whether at the end of the day there'll just be one system where it all works, or whether things will just get too big, I've got no idea. I've got no idea if we're going to have proved it in 10 years. I've got no idea if other mathematicians are going to become remotely interested. I see a whole bunch of people in the number theory seminar who are currently not remotely interested, and I don't see any reason why they should get interested, because I'm just proving something that they know already.
It's your dress style.
But we need some kind of application, and I don't think proving Fermat's last theorem is that. I'm doing it for purely self-centered reasons.
Well, you have been probably the most successful popularizer of formal math, formal math in the last.
Yeah, but that doesn't mean that everyone's going to do it, right? It might just be a niche. There's plenty of people who are good at popularizing X, but it doesn't mean that everyone does X. It just means that there's a nice X community. And I don't know if there's going to be I don't know if all mathematicians are going to be formalizing. I think that might be asking a lot. And unless we really give them a tool, then I don't think we're not remotely ready to give them that tool yet. The automation proves, people were talking about don't understand what automation's doing, and that's just not remotely an issue as far as I'm concerned, because the automation can only do things which I regard as totally trivial. We don't even need to understand what the automation's doing.
As long as it's sound.
So as the, like, I don't know, social person, like, do you have any estimate what the curve is now? Like, is it still exponential? Like the number of lean Zulipers, or?
Probably look at the numbers or something. I mean, there's a healthy amount of people on the lean. There's a huge amount of discussion happening on the lean chat, which is great. But I just.
Okay. It's trending up a little bit, but it's closer to linear than quadratic at this point.
Okay. The exponential phase is over. Okay. Peter.
Well, I hope that you will say the final words.
No.
So I would just like to say one aspect which probably has something to do with what Florian said. I think a big question is, will sort of formal methods in computer science develop so far that checking mathematical proofs can be a byproduct of those systems. And this may be quite dramatic or drastic for mathematicians who love their old styles and practices. And I think one argument for having formal mathematics within math departments is perhaps to do something against that possibility or danger, or however you might term it. So I think it's quite an interesting question, and I think I'm also very happy about the big contribution of mathematicians, especially in the lean big project, that this sort of is done by young mathematicians, and I hope that is sort of continuing and will be successful. Yeah. So, assuming that this is all successful, then yeah, let's be optimistic. Yeah.
So, formal math will be how many % of math 20, 30 years from now?
Well, it probably depends on how this community organizes things, yeah, how we present ourselves in mathematics, whether we can sort of perhaps present something uniform or something which through some translation mechanisms can bridge between the various systems, didacti or whatever, I don't know particulars there, so that we can sort of present a strong, that we really can talk of formal mathematics, whereas at the moment I still think it's quite split up into various communities.
Okay, looks like I will not get bold predictions from these people. Thank you.